Add another approach that we might employ in order to make this code faster. Let's take a look at multiprocessing. Again, we have our starting program, and for our starting program, why don't we make a couple of small changes to it, and then think about how we can employ multiprocessing here. The changes we'll make, of course, are to remove this explicit print statement, to group together these two pandas functions, to turn this into a logger.info, like that. And that's probably good enough for what we need. There we go. The other change we're going to do is we're going to add some timing to these. So here, this is getting the jobs. This is getting the results, or sorry, this is getting the status. Sorry, let's fix this up. This is getting the status. This is getting the results. Up here, we're actually getting the job listing, which we anticipate that there's really not much that we can do about that. There's only one API call, and there's really not much we can do until that API call returns. So it'll be the case that there are some things we just simply have to wait for. There's no way to get around it. And here is our pandas code. In the case of multiprocessing, what we're going to do is we're going to start up one process for each unit of computation. Because the global interpreter lock's scope is that one Python process, if we start up multiple processes, then we have multiple independent global interpreter locks which do not interfere with each other. And so, unlike in the Asyncio or the threading circumstance, the multiprocessing circumstance will actually give us the ability to speed up part of this program that we had otherwise thought might not be amenable for speed up. Specifically, the pandas work down here. Here's what I'm going to do. To make my life a little bit easier, I'm going to take the job results that we have, and I'm going to go into the pickle module. I'm going to dump this. Let's do a couple of small things. Let's pull in exit from the sys module. Set that there. And then from the pickle module, let's import dump. Let's actually do the loading up to when the first three results finish, and then we'll take a look at the pandas code by itself without having to pay that 14 seconds or 15 seconds of cost to do the initial loads. So what I'll do is I'll say with open temp results.pkl. I'll do this in writing binary mode as F. I'll dump job results to this, and then I'll actually do a load just so that I can show that this round trips. Like that. So here we'll read that in. So that should prove that I can pickle this and round trip it. If this works, then I can tear off just that one portion of the code without having to pay the cost of all of the upfront points. This pickling trick just really helps us tighten up that iteration loop and really don't want to be waiting 15 seconds just to see whether a one-line change of code here works. Now, of course, in order to make this work, we have to spell everything correctly. And you can see why having that very loose iteration loop, even 15 seconds, is so painful. One typo just wasted us 15 total seconds, but it's an opportunity for us to take a sip of tea while we wait. Okay, when this returns, we should be able to tear off just this one portion, and we can see whether or not multiprocessing will allow us to improve the computational speed of the number crunching operations, the compute bound portion. What I'll do is I'll say, here, we'll grab from the pickle module, let's grab a couple of our imports from above. In fact, we'll grab all of our imports from above, and we'll just grab this block of code here and think narrowly, can we improve this? Similarly with threading, it is the case, and we need our logger as well. Similarly with threading, it is the case that multiprocessing can be more surgically added to a program than Asyncio. probably it is likely to be the case that we do want to think about whether our program will eventually be multiprocessing or eventually be threading from the very beginning. But there are circumstances where if we need to speed something up in a very narrow case, can we isolate the part of the program, spin up a bunch of threads or a bunch of processes and see what works? I'm actually going to try doing that with our concurrent.futures approach. So let me get my load and dump from Pickle, and let's think how this would look. What I want to do is I want to create a multiprocessing process for one of the compute-bound portions of this. And I think one of the compute-bound portions here is going to be this group by apply operation. What I do when I take my data set is I group it by categories, and then I pass each of those categories to this apply that's doing some computational work. What if I take the actual number crunching and put that into a separate process and see if I can get a speed up on my 8 seconds? Now, for those of you who know the answer to this already, you know that in truth, for an operation that is as simplistic as a grouped weighted summary statistic, there is a way, without reaching for any of this stuff, to make this about 1,000 times faster, making use of just a little bit of Python dropping down to the NumPy level. But we'll pretend that this operation is just marginally more complex than our grouped weighted summary statistics strategies can adopt, and we'll see whether multiprocessing can help us here. With multiprocessing, very similar to threading, I have some target, some Python function that'll be run in each process. That can, of course, take arguments. I can create a pool of these processes. I can start each one of the things in my pool. And of course, I definitely want to wait in the parent process for all the child processes to complete, like that. Here, we can print out the name of this process here. And of course, we'll need to pass in some keyword arguments. And so here we'll say this is process number X. So we should have 3 processes. If it's the case that we need to pass data between these, we cannot use a Python list. We cannot use a collections.dec. We cannot use a queue.queue. Fundamentally, each one of these callbacks is being called in a separate process. And as we know, the unit of isolation in a Linux or Unix-based operating system is the process. These processes do not share the same memory space. In fact, they have clones of the original parent's memory space. This means that a couple of small conceits that we've already done are actually going to give us some weird values if we try them here. One thing that I've done very regularly through all of the examples we've looked at is to create an instance of this seeded random state and then to use it within the targets. Take a look at what happens here. If I do a rand range, let's do a rand range 100,000. How on earth did let's do this with 30 of them. What is the chance that randomly picking a value from 1 to, not 100,000, let's really make this fun. Let's do 100 million. What is the probability that 30 separate processes randomly picking a value between 0 and 100 million all come to the same value? This is a very common mistake that people make with multiprocessing. What happens when you start up that process is it will take the memory, the image of the current parent process, and it will clone it into each one of these child processes. And those child processes will pick up running just the function that you specify as the target. That means that each one of those processes will appear to have a shared global state. For example, if I do something like jobs equals A, B, C, and I also look at the jobs here, it'll look like they all share the same global state, A, B, C. But in truth, what's happened is they all share that global state as it existed as of the spawning of the processes. In the case of that random object, they all shared the state of that random number generator that was seeded as of the start of this process, which means if these individually then go and ask for more random numbers, they will end up passing through this pseudo-random number generator, they'll end up passing through each one of the random values that this thing will give you in the same order, and we'll get the same random values. So it's very important that we are careful about how we use anything that looks like global shared state in the multiprocessing regime. For example, if we have a random object, we need to make sure these are seeded. Probably in this case, we want to seed them differently. So we might do something like this. Otherwise, we'll start getting weird results. All of our processes that might need to have their own randomness won't appear to have their own randomness. So here, I'll seed these like this. And there, we'll actually get some real randomness. And if we need to share data between these, we cannot use a q.q. We cannot use a collections.dec or a built-in Python structure because they simply won't share. We have to use a multiprocessing.q. Behind the scenes, what the multiprocessing.q is going to do is it's going to take anything we put into it, and it's going to send it to all of these processes by pickling that data and unpickling on their side. So here, if I have some queue of the jobs that I've seen, I'll have to do something like this, and I'll have to pass it down to each one of these, like that. So let me show you a simple producer-consumer for our multiprocessing approach. For the multiprocessing approach, a producer-consumer might look like this. Here, this gets our jobs. We'll run forever. We'll maybe sleep for a moment of time in between here, and we'll put into this thing a name, which will randomly generate. Here, we'll seed a random number generator with, or actually we'll not see the random number generator so that this thing will no longer be deterministic. We'll choose from, of course, ASCII lowercase. And I'm feeling lucky, we'll do 4-letter names from ASCII lowercase. I have never run into trouble with a work inappropriate 4-letter name randomly generated. Maybe if I don't see this random generator today is going to be the first day. But we'll see if that works. Then for our consumer, of which we'll have a couple of these, we'll say, okay, while Q is not empty, what we'll do is we'll do a while jobs is not empty. We'll get something from this. I think we can set a timeout here. Here we'll say if we actually got something from this, otherwise we'll get a none. We'll just print out processing that. Okay, very good. Now our pool will be one producer. And of course, we'll pass in our keyword arguments. Jobs will be some shared multiprocessing.q object, and we'll do a couple of consumers. Sorry, this is process, and this will be our consumer here and our consumer there. One producer, 2 consumers. We'll go through each thing in the pool, start them up, and we'll wait for them to all complete before we're done. And here we can see, and we should actually tell these things. We'll give these an identifier. So this is consumer 1, and this will be consumer 2, just so you can see that this thing works as we expect. Very good. And here, like that. Now let's see what we did wrong. This is, oh, and of course we actually need to do this as a while true. Otherwise, the moment the thing is empty, these consumers terminate. So we'll just do this as a while true like that. Okay, very good. Here, this actually doesn't give us a none value. This actually will raise an exception. So this is what a queue empty. Okay, so here, otherwise, we'll actually process this. Okay. I think it might be from the queue module where you have to pull this. Okay, there we go. So you can see here we have our formulation. Passing data between multiple processes is tricky. Remember, In the threading.thread example and in the async IO, we have one process, which means we can pass things in the global scope. It just comes down to, do we need to lock it or not? In the multiprocessing approach, we have to use very complex tools like that multiprocessing.q, and we are limited by what we can pass around.